Hi everyone, section 3.6, the chain rule. This is a rule that we have been leading up to for a little while now, and we've seen in small bits and pieces in previous sections. It's a way of finding dy dx indirectly, because we might be able to find dy du, and we might be able to find du dx, but we can't find dy dx directly. So what we do is we take dy du, and we multiply it times du dx to give us dy dx, because the du's cancel. And we've seen this back in section 3.4 in example 2, when we solved this problem by finding dy du and du dx. We multiplied 2 times 3, and we got 6. If we look at this example here, we can take the derivative of this y function using the power rule, and we would get 36x cubed plus 12x. But what if this function were factored? Okay, is there another way to find this derivative without having to multiply it all out into the expanded form and find the derivative using the power rule? The answer is yes, and that's using this chain rule. And this is going to be useful for functions where we don't have the option to even expand it. So this is just going to illustrate how we're going to do it. So what we do is we take a look at what is the inside function here. The inside function here is 3x squared plus 1. We're going to call that inside function a new function. We're going to call it u. We'll call it, so 3x squared plus 1 is equal to u. So that means that what's left is the outside function is the squared function. So y, the original function, is equal to u, the inside function, squared. We can find the derivatives of each of these. We can find dy du with respect to u. We can find du dx, the derivative with respect to x, pretty quickly. Dy du is 2u, power rule. Du dx, 6x, pretty quick. If we multiply dy du times du dx, we're going to get 2u times 6x, or 12ux, but we know what u is. We defined u as 3x squared plus 1. So what we really have is, if you multiply all this out, 36x cubed plus 12x, the same result that we got if we had used the power rule. And again, it would have been quicker to use the power rule in this problem, but we don't always have that option. Okay, so this is called the chain rule. You're going to want to fill in the official chain rule here. And let's get into example 1, where we're going to apply the chain rule. So we're going to have our inside function is 3x plus 5, and our outer function is raised to the 17th power. So if we go we define u equals 3x plus 5, and y is now equal to u to the 17th power. We can find dy du is equal to 17u to the 16th power, taking the derivative of this function with respect to u. Take the derivative of this function with respect to x, du dx is equal to 3. And we're going to multiply these together. Dy du times du dx. I'll do that over here. Dy du times du dx. And after a while, we're not going to have to write out all of these steps. Noticing that those are going to cancel, the du's cancel, which is what leaves us with dy dx, is what we're looking for. Okay, so dy du, 17, write that down, 17 u to the 16th power times 3. So dy dx is equal to 51 u to the 16th, but we know what u is. U is 3x plus 5. So 51, 3x plus 5 to the 16th power. Okay. Another way of thinking about this is the inside-out or outside-inside rule. Take the derivative of the outside function. 17 goes down, subtract 1 from the 17, make it 16, and then multiply that times the derivative of the inside function. Derivative of 3x plus 5 is 3. 17, 3x plus 5 to the 16th times 3. 3 times the 17 gives you the 51. It's just another way of thinking about that. You do want to watch these two videos here from Calculus with Krista. Example 2, dy dx. Here's an example where we could not expand this. That we have the outer function is cosine, the inner function is x cubed. Okay, so y prime, dy dx. Let's be consistent with my notation. Dy dx is equal to, what's the derivative of the outer function? What's the derivative of cosine? Well, the derivative of cosine, we know from section 3.5, is negative sine. So minus 4 sine x cubed times the derivative of the inner function. What's the derivative of x cubed? 2x squared. So our final answer sorry, 3x squared. Negative 4 times 3, negative 12 x squared sine of x cubed. Example 2. Example 3. We want to find dy dt at t equal to negative 1. So we're going to evaluate our final answer by plugging in negative 1 in for our t value. So we want to find dy dt if y is equal to x cubed plus 5x minus 4 and x is equal to t squared minus 1. We could plug this t squared minus 1 in here and in here. We could cube out the t squared minus 1. We could multiply the t squared minus 1 times the 5. We could combine all the like terms into power rule. Or we can do chain rule. We can find dy dx, the derivative of y with respect to x, and dx dt, the derivative of x with respect to t. Let's do that. Dy dx is going to equal 3x squared plus 5, and dx dt is going to equal 2t. So dy dt, let's multiply these two together. Dy dx times dx dt equals 3x squared plus 5 times 2t. So dy dt equals, and we know what x is. Okay. 3 times t squared minus 1 squared plus 5 times 2t. And we want to evaluate this, now that we've got this, at t equaling negative 1. So we'll put negative 1 in place of all the t values. let's see, dy dt is equal to 3 times -1 squared minus 1 squared plus 5 times 2 times -1 . Probably should have used fancy brackets and bigger brackets, but let's go 3 times -1 squared is 1, minus 1 is 0, squared is 0, plus 5 times -2. 3 times 0 is 0, plus 5 is 5, times -2, -10. There's our answer to example 3. Example 4. This time we're just finding dy dt, dy dx. This time we're not going to be evaluating. So dy dx, we can find the derivative of y with respect to t, dy dt. We can find the derivative of t with respect to x, t dx, and then multiply those together. So dy dt is equal to 3t squared. dt dx is equal to 2x. Multiply these together. dy dt times dt dx equals 3t squared times 2x. We know what t is equal to. It's equal to x squared minus 1. So we're going to replace the t here, the x squared minus 1. We're going to get dy dx equals, I'm going to distribute, so 6 x squared minus 1 times x, or dy dx equals 6x x squared minus 1. Final answer. That was example 4. Example 5, down over there. Example 5, if f of x is equal to the square root of t plus 2, and t, which is equal to g of x, is equal to x cubed minus 1, then we want to find the derivative with respect to x of f of g, the composition of the functions f and g, when x is equal to 2. We're going to evaluate this when x equals 2 in the end. So we want to find dx of f function composed, the g function. Another way of writing that is f of g prime. So Leibniz's notation, Newton's notation. And if we use the outside-inside rule, we do the derivative of the f function times the derivative of the g function. So the f function, which is, do I want to do that off to the side? Yeah, let's do that off to the side here. F prime of x is equal to, let's rewrite f of x first, actually. F of x is equal to t plus 2 to the 1/2 power. So f prime of x is equal to 1/2 t plus 2 to the negative 1/2 power. Bring the 1/2 down, subtract 1, we get negative 1/2 here. Another way of writing this, this is probably the best way of writing, yeah, would be 1 over 2 square root of t plus 2. Negative exponents become positive when you move them down. Fractional exponents are radicals. So this is f prime. So 1 over 2 square root t plus 2 times the g function. The derivative of the g function is easy. I don't have to even write that out off to the side. That's just going to be 3x squared. And we want to evaluate this when x equals 2. Okay? Keeping in mind that we know what t is equal to. T is equal to x cubed plus 1. So, one more time. 3x squared over 2 square root x cubed minus 1 plus 2 evaluated at x equals 2. So I'm going to plug 2 in for all this. This is really just 1. Can we remember that? 2 squared is 4 times 3, 12. 2 square root 2 cubed is 8 plus 1. How convenient. 8 plus 1 is 9. Square root of 9 is 3. 3 times 2 is 6. 12 divided by 6. Final answer is 2. And all is said and done. All right, example 6. We want to find dw dt. So we can find the derivative of w with respect to x. We can find the derivative of x with respect to t. So dw dx times dx dt will get us dw dt. So dw dx is equal to the derivative of tangent. What's the derivative of tangent? Is secant squared. And dx dt is equal to power rule 12x squared plus 1. T squared, sorry. So dw dx times dx dt equals secant squared x times 12t squared plus 1. And we know what x is. X is 4t cubed plus 1. So we can replace this x. And then we put this out in front. 12t squared. And this is dw dt, derivative of w with respect to t, plus 1, times secant squared of bracket of 4t cubed plus t. And that's the answer to example 6. Power chain rule is a combination of power rule and the chain rule together. Example 7. has two different ways of solving this. Bring this up closer so I can make sure that I get this right. So let's do chain rule method. A would be, what is the f function? F of x is equal to let me write it as u. F of u is equal to u to the 35th power, and g function, inside function, is equal to x cubed plus 7x plus 1. Okay. The derivative of f prime of u is equal to 35 u to the 34th power, and g prime of x is equal to 3x squared plus 7. And dx of the original function, x cubed plus 7x plus 1 to the 35th power, is equal to f prime of u times g prime of x. F prime of u is 35 u to the 34th power times g prime of x, 3x squared plus 7. U is the u, the original inner function, is x cubed plus 7x plus 1. So we have 35 times u x times x cubed plus 7x plus 1 to the 34th power times 3x squared plus 7. Okay. Method B is to do derivative let's call f of g of x equal to x cubed plus 7x plus 1 to the 35th power, and f of g prime of x is equal to f prime of g of x times g prime of x. Derivative of the outside function times the derivative of the inside function. Derivative of the outside function evaluated at the inside function times the derivative of the inside function. So, derivative of the outside functions, take that 35, put it out in front. Power rule, 35 x cubed plus 7x plus 1, inside functions untouched, to the 34th power, subtracting 1, power rule, times derivative of the inside function, 2x, sorry, I keep doing that, 3x squared plus 7, and there's your final answer. Same answer that we got over here using the u's. It doesn't matter which method you use, whether you think of it as outside inside or chain, you're going to get the same result. Example 8. Let's do outside, inside. So dx cosine x squared plus 9 equals derivative of the outside function. Derivative of cosine is negative sine of the inside function untouched times the derivative of the inside function, 2x. Simplify this, negative 2x sine x squared plus 9. Example 9. Let's do it the same way. dx tangent squared x equals. What's the outside function this time? So the outside function in the previous problem was cosine, and the inner function was x squared plus 9. This time the outer function is 2, is the power squared. The inner function is the tangent. So the outer function is the power rule, 2 times the inner function untouched, subtract 1 from the exponent, times the derivative of the inner function. The derivative of tangent is secant squared x. Final answer, 2 tan x secant squared x. That's example 9. Example 10. Slide this up here. Example 10 is going to be easier if we rewrite the y function. We're going to rewrite the y function so that y is equal to 2x to the 4th minus x squared plus 8 raised to the negative 1 power. We could do quotient rule, but it's not worth it. This is actually easier. This is now a chain rule function. Outside function is negative 1 power. Inside function is 2x to the 4th minus x squared plus 8. We could turn this into the u function, but let's just do it in our heads at this point and say dy dx is equal to d dx of 2x to the 4th minus x squared plus 8 to the negative 1 power, which is equal to power rule, negative 1 comes down in front, negative 1 times the inner function unchanged, 2x to the 4th minus x squared plus 8, power rule, subtract 1, so negative 2 power, times the derivative of the inner function, 8x cubed minus 2x. The rest is just cleaning it up. Let's distribute. This is going to move down to the denominator because we've got the negative exponent. The negative 1 is going to distribute through the numerator, so I'm going to get 2x minus 8x cubed in the numerator, and the denominator is going to become 2x to the 4th minus x squared plus 8 to the positive 2 power. That's example 10. Example 11. So again, chain rule, we're going to have more than one step in this chain, more than one link in the chain, if you want to think of it that way. So the first most outer function is the cubed. Then the function inside the cubed is the sine. Then the function inside of that is 9x plus 1. So we're going to have multiple layers to this chain. Dx sine cubed 9x plus 1. I'm going to write out each level of this chain this time. It's going to equal the derivative of power is going to be 3. Next function unchanged, sine 9x plus 1. Subtract 1 from the exponent, so squared, times. The next function down is the sine function. So derivative of the sine function is cosine function. So I'm going to write that. dx of sine 9x plus 1. I'm going to do it in stages. You don't have to do this in stages, but just to illustrate, I'm going to do this in stages. This is another chain rule. So derivative of the sine is the outside function. 9x plus 1 is the inside function. So 3 sine squared 9x plus 1 times derivative of sine is cosine of the inside function unchanged times ddx. Consistent, stick with my brackets, of the inside function, which is 9x plus 1. So I still have one more derivative to take. The derivative of 9x plus 1 is 9. 3 sine squared 9x plus 1 times cosine 9x plus 1 times 9. And our final answer, 27 sine squared 9x plus 1 cosine 9x plus 1. Example 12. I'm going to change this, rewrite this as y equals 3 plus secant pi x to the 1/2 power. And we're going to see, again, we're going to have multiple layers. First function is going to be the power function. Second function on the inside is going to be secant. The next function inside of that is going to be another power function. Most people forget this last one. dy dx of, I'll leave it written with the square root, even though we're going to use this. 3 plus secant pi x equals power function, power rule, 1/2 times inside function unchanged, untouched, 3 secant pi x, subtract 1 from the power, times dx of the inner function, 3 plus secant pi x. Derivative of 3 is 0. Derivative of secant, let's rewrite this, 1 over 2 square root 3 plus secant pi x times derivative of secant is secant x tan x, so secant pi x tan pi x times d dx of the inner function. There is one last inner function here, and it is pi x, which is one more power rule. So in the end, derivative of pi x is pi. So in the end, you get pi secant pi x tangent pi x over 2 square root 3 plus secant pi x. That's our final answer for example 12. That was a pretty good problem. It leads us into our challenge problem. The challenge problem is only a challenge because you got to keep track of the layers and the chains in our chain rule. So d dx cosine squared 1 minus x plus square root x plus 3 all to the 5th power. So, what's the outermost function? Outermost function here is the 5th power. 5 cosine squared 1 minus x plus square root x plus 3 to the 4th power times d dx of the new inner function, which is now cosine squared 1 minus x plus square root of x plus 3. Derivative of this is addition, actually. Power rule, chain rule, chain rule, power rule, chain rule. A lot going on here. So let's carry down. I'm actually going to slide over the 5 cosine squared 1 minus x plus square root of x plus 3 to the 4th times. First function here, power rule, 2 cosine 1 minus x times d dx of the inner function, cosine of 1 minus x. Got that so far? So I took the derivative of this plus derivative of this. So I'm not going to rewrite it, but this is a 1/2 power again. So 1/2, 1 over 2 square root x plus 3. We've seen that a few times today. So I'm just jumping straight. We saw it right here where we did that. So I'm just going to jump right down to this part of the answer a little bit quicker. Times d dx of the inner function x plus 3. Derivative of the inner function. Getting closer. 5 cosine squared 1 minus x plus square root x plus 3 to the 4th power times, my 2's cancel here, I believe. No, they don't. Sorry, we have a plus in between them. So I'm going to leave that. 2 cosine 1 minus x. Derivative of cosine. Negative sine. of 1 minus x times d dx of the inner function, 1 minus x. Plus derivative of x plus 3 is 1 over this. So 1 over 2 square root x plus 3. This, I'm going to make fancy brackets this time. Is all being multiplied there. Okay, so we have one more derivative to take, and then maybe a little bit of cleaning up to do. So the derivative here is -1. Coupled with this negative sign, it's going to become 5 cosine squared 1 minus x plus square root of x plus 3 to the 4th bracket. This is now going to become, so negative times negative, positive 2 cosine 1 minus x sine 1 minus x plus 1 over 2 square root x plus 3. And that is our challenge problem, example 13 in this section. Some IXL problems for you to work on and some bookwork. Thank you very much. Bye.